Okay, so all I've asked you to do is expand each of these brackets and simplify them. So what would the first one be? A plus b to the power of 0. Just be 1, okay? Anything to the power of 0 is 1, regardless of what that thing is. Right. What about a plus b to the power of 1? A plus b. Good. So far, so good. This one's not too bad. A plus b to the power of 2. Yeah, good. Plus 2ab plus b squared. What about this thing? A plus b all cubed then? Okay. Perfect. Okay, good, well done. How did you know that? How did you get that? So how did you know that that was equal to that? It is right, but how did you know? Absolutely right. So you said that this thing here should just be this one, a plus b all squared, times by another a plus b. So in other words, if you take this thing and times it by another a plus b, you should get this after you've simplified everything in place. Okay? Has anybody had a go at the last one? Okay.
4a cubed b.
Good.
6a squared b squared.
Perfect. So all you're doing there really, aren't you, is you're taking the previous one
And the same.
and timesing both.
Is that b?
Yeah, okay.
Is that correct?
So what do you mean the same?
A power 4 plus 4ab cubed.
Good.
6.
I think you're fine. I think you're finished.
No,
Yeah, I think you're finished there. Yeah? Yeah, good. So all you've done there is you've taken this one here, will just be taking the previous one and timesing by another a plus b. And this is what you get after you've simplified it. And you can carry on doing this, okay? So to get a plus b to the power 5, you just multiply every single term in here by a plus b, and then you simplify, okay? Now, what I'm doing here is something called a binomial expansion, all right? Now, can anybody think, why is it called a binomial? Why is it called a binomial? I mean, I get expansion because I'm getting rid of brackets, okay? And when we get rid of brackets, we're expanding. That's the algebraic operation. But why is it called binomial? What does that mean? Yeah, good. So you're seeing bi there, thing like bicycle, okay, means 2, okay. And nomial, well, the nomial actually means a named object. So in this case, my named objects is a and b, or a and b, yeah? So in this case, I'm looking at my named objects are just a term, okay? So a binomial in this context simply means that I have 2 terms. And I'm expanding them out. I'm seeing what happens if I take these 2 terms, a and b, and I raise them to higher and higher powers. Okay, and this is a kind of pattern that we get. So what I want to do then is I want to say, what happens if I raise this thing to any power I like? Can I generalize it? Can I generalize it? So just raise it to any power I like, what happens? Okay, good. So you're seeing some kind of pattern here. So maybe look at these, okay? Maybe look at these. Let's go through. Don't worry about the numbers in front. Don't worry about the coefficients for the time being. Let's just look at what happens with the a's and what happens with the b's. So if I pick that one there, for example, a plus b to the power of 3, let's watch what happens to the a's. Are you happy we start with a cubed? That's my first term. My second term goes a squared. My third term goes a to the power of, well, 1. And this term goes a to the power of 0, because of course a to the power of 0 is just 1. Okay? So what do you notice about the a's, or the powers of a's? They're decreasing with every term. Okay? So the powers of a's are decreasing. Okay? Now let's go back and have a look at the powers of b's. Okay? Well, are you happy there is a b hiding there? What is the power of b there? 0, right? Because b to the power of 0 is just 1. okay? What's the power of b here? 1. And then we go b squared, and then b cubed. So what's happening to the b's? Yeah, the b's are increasing. So you're kind of getting this inverse relationship going on. The a's are going up, and the b's are going down, okay? Now you're happy this thing is completely symmetric, so it doesn't actually matter which order I do things in, as long as one's going up and one's going down. Okay? It doesn't matter which one goes up and which one goes down, because you'll get the same result if I'd written this in the other order, like reverse the order. Yeah? All right. And you can see the same kind of thing happening here, like a to the power 4, a to the power 3, a to the power 2, a to the power 1, a to the power 0, and b to the power 0, b to the power 1, b to the power 2, b to the power 3, and b to the power of 4. So my next question is then, we've established what's happening with the a's and what's happening with the b's. What's happening with the numbers? What's happening with the coefficients? Is there any way that we can figure this out? Well, in fact, let me write out the coefficients in a different way. So are you happy that we start off with the first coefficient is just 1? Okay. What are the coefficients of each of these?
1.
Just 1, right? So I'll put them in. So the next row would be 1 and 1, so a plus b to the power of 1. What's the next row? So what's the coefficient of the next row?
1 to 1.
Good. 1, 2, 1. You happy? Okay. What are the coefficients of the next row? Good. 1, 3, 3, 1. What are the coefficients of the next row? 1, 4, 6, 4, 1. Perfect. What do we notice? Does anybody recognize this particular triangle which I've drawn here? Yeah, good. So to get any element in this triangle here, I just take the ones which are immediately diagonal above it. Okay, so you see here, I got 6 by adding 3 and 3. Yeah? I got 4 by adding 3 and 1. I got 2 by adding 1 and 1. Does that make sense? Yeah? So in fact, let's go for a plus b to the power of 5. All right? Let's see if we can expand this out without thinking about it as taking a plus b to the power 4 and multiplying by another a plus b. Okay? So you're happy. What's going to happen with the powers of a's, first of all? So good. Plus a to the power of 4 plus a to the power of 3 plus a to the power of plus just a. And then there'll just be a plus a to the power of 0, but I'm not going to bother writing it in. The b's then, it's going to go b to the power of 0, then b to the power of 1, or just b, then b squared, then b cubed, then b to the 4, and then we're going to finish off up at b to the power 5. So b to the power 5 corresponds to that. We don't go any further than that. Okay? So let's think about what the numbers are going to do. We can work this out by finding the next row of this triangle. So you're happy the outer ones have got to be 1, like the pattern continues like that. What's the number that goes here? 5. So I'm going to put a 5 in there. Okay? What's the number that goes there? 10. So I'm going to put a 10 in there. What's the number that goes there? 10. Perfect. So I'm going to put 10 there. Number that goes there? 5. Good. So I'm going to put 5 in there. And of course, the outer two are just 1. Okay? So you're happy that's the next row in this expansion. Okay? Does anybody know the name of this particular triangle? It's quite a famous triangle. Do you know who came up with it? Well, actually, he didn't come up with it. He just made it famous. It's called Pascal's triangle. Okay, named after the French mathematician, Blaise Pascal, which I think Blaise is quite a cool name, right? I think that's right. I think that's how you spell it, at least. He was definitely called Blaise Pascal. I don't know, I'd quite like to be called Blaise.